Hello everyone and welcome to this lecture on the chain rule for multiple variables. So gonna cover the chain rule today. It's an amazing topic. Let's just add this so I can write some notes for you to see. So the chain rule. Suppose that z equals f of y, the differential function of x and y, where x, so this is the function z, and say x equals g of t and y equals h of t. These are different functions of t, and they're both also differentiable functions of t. Then z is differentiable function of t, such that this easy. Let's break it down. It looks like a big formula, but basically it's it's way more simpler than you think. So it's basically dz with respect to dt. So we cannot do that directly, since z is in terms of f of x and y. So you can see z is function of x and y, so it can be like x squared plus yx plus x to the 3 plus whatever. This is z. Okay, and we don't have any t in these functions. We just have these functions x and y. We have them as another function of t, say t squared plus t to the 3 plus whatever, and then this is t over t plus 1 plus e to the t and plus other terms. So these are functions of t. Z is functions of these functions. So, and it would be a bit hard to just go on. Okay, I know some of you would think that, okay, why not substitute x and y into z and then try to differentiate that? Okay, that's a reasonable thing, but if you're gonna try that, it's gonna be very complicated, especially if x and y are very long variables, or variables that have a lot of terms. It's gonna be very it's gonna make it hard for you, and you don't want that. So in order to make it easier for us, mathematicians developed the chain rule, which states that if you want the derivative of a function with respect to another variable, okay, and that function, that z is a function of another two variables of that function, so basically you're gonna have the partial derivative of f with respect to x, which is fx, okay, and then multiplied by dx. This is not a partial derivative, this is a regular derivative, dx with respect to dt, since we don't have any other variables anyways. So yeah, we're gonna have the normal derivative. It's just a function of one variable, and yeah, plus the partial derivative of f with respect to y, which is fy, multiplied by dy over dt. So this is dy over dt plus dx over dt is basically dz over dt. So this is also a regular derivative, since it's of one variable. And this is the chain rule. This is basically the chain rule. Very easy. Let's see some examples. I know most of you don't. They want examples. So now we have w. W is a function of p, function of q, and a function of r. And we have p as a function of t. We have a q as a function of also t. And we have r as a function of t. As a function of t. So, and we want to find dw with respect to t, and we don't have that, so we're gonna, and if we try to substitute, it's gonna give us a very complicated, we're gonna multiply cosine 3t squared by t over t squared plus 1, and we need to differentiate that inside the exponential, which give us a lot of trouble, and we don't want that. And also we need to apply the product rule, since p is another function, so it's gonna make our lives way harder. So let's do it the chain rule way. state the chain rule. T equals W respect to P. Then okay, so we need more space. So dW over dt dW over dP, then dP over dt plus partial derivative of W with respect to Q, then dQ over dt, multiply that, and then we have partial derivative with respect to R, dr over dt, and we can easily find the derivatives for those. dW over dt, we're gonna have the partial derivative with respect to B is basically e to the qr multiplied by dv with respect to t, 1 over 2 square root of t, plus dw with respect to q is just rp e to the qr, taking every other variable constant, multiplied by q with respect to t is just 60 minus 60, multiplied by minus 60 minus 60 sine of 3t squared, and then respect to r, pq e to the qr, multiply that by dr with respect to dt, which is the quotient rule, 1 times t squared plus 1 minus t times 2t over t squared plus 1, and this is basically the partial derivative or the derivative of w with respect to t. If we want to simplify that, we can do that. And also if we want to substitute the values for qr and also p, we can do that since they are all functions of t, so we get a pure function of t. But I'm not gonna do that because it's gonna make my life harder, and I don't want my life to be harder. So now we have the chain rule, which is the second case. First we covered case 1. What is the second case? What is case 2? Suppose that z is also a function of x and y as differentiable function of x and y, where x equals g, which is a function, x is a function of s and t, and y is a function of s and t, are differentiable functions of s and t. And so we get something different this time. We get something different. Now, so the first case, okay, let's show you what's the difference between the first case and the second case. I think you noticed it. The difference is very simple and clear. Here x is a function of one variable t. Y is a function of one variable t. However, for the second case, if we noticed, x is a function of two variables s and t. Y is a function of two variables s and t. And so if we want to find the derivative of z with respect to one of these variables, we're gonna write one equation. And if we want to find the derivative of the function with respect to another variable, we're gonna have another formula. So it's two variables. If we have three variables, we're gonna have three formulas. If we have four, we're gonna have four formulas. It's gonna get even more complicated, but this is basically it, and it's basically the same concept. So we're gonna have more partial derivatives, since now we are not talking about one variable for each of y and x. We're having more variables, so we're gonna use the partial derivative. So for the first one, we want to have the partial derivative of dz with respect to the one of the variables, which is s. We don't have z as written as in terms of s, so we need to do something, which is the chain rule, basically dz with respect to dx. This we have, okay, the partial derivative, since we have z as a function of x, y, but we're gonna take the partial derivative with respect to x, and then the partial derivative of x with respect to s. So, and notice that x now is a function of two variables, so we need a partial derivative. Can't have the regular derivative, okay? And the same here, dz with respect to dy, the partial derivative with respect to s, and then same concept goes to the t, to the other variable st, w, z, whatever you call it. And so we have example 2. Let's solve an example. Guys, we love examples. Examples give us very or it gives us like a way to solve yeah, gives us a way to solve. Okay. Let's go here, insert our little photo, add, love it. Z equals 2x to the 3 y plus y squared plus 5, and we have x equals s cosine of t squared. We have y equals e to the s squared plus t squared. Find, okay, why am I rewriting this? Because I don't like the font, the original font, for some reason. Okay, so did I forget the formula? No, I didn't. Okay. So dz with respect to ds. So we have partial derivative of z with respect to x. Whereas z, partial derivative, that's very why? It's very, at x with respect to s. Cosine. This is the cosine of t squared. Okay. Plus ez with respect to y, 2x to the 3 plus 2y. Multiply that by dy with respect to s, which is 2se to the s squared 2t, and that's very easy. But now wait for the easiest. dz with respect to dt. Now this is a different story. But similar. It's not very different, but it's similar. We're just gonna need to change the variables a bit. dz with respect to dt. I wanted to solve some of the examples I'm giving you. Please, you need to solve them. And that's for a very well-known reason. You know it, I know it, we all know it. We all know why we need to solve these examples. Okay, 6x squared y times dx over dt with respect to t, so it's minus 2t s sine. Okay, I hope this doesn't get confusing. T squared. Okay, this is the first part, we're done. And then with respect to y, we have 2x to the 3 plus 2y. And then we take dy with respect to s, gives us, with respect to t, gives us 2t e to the s squared plus t squared, and like that we have finished the example. Very easy. I love it. I love the chain rule. I thought this was harder, but to be honest, that's way more similar, I think. And this is basically shows us how the variables branch. So z goes to the partial derivative of z with respect to x, partial derivative of z with respect to y, and it branches to x and y. Partial derivative of x with respect to s, x to t, y to s, y to t. Then it gives us two s's, two t's. If you have more variables, this is very interesting. I love this. W goes to x, to y, to z, to t. Now these branches, I love them. Now if we have three variables, it's gonna be more. It's gonna be u, x, y, r, s, t. So it branches. And now we arrived at the general chain rule. What is this? This looks very complicated, and I agree with you if you say this is very complicated. But if you say this is not complicated, then you are a very smart person. The chain rule. The general version. Suppose that u is a differentiable function of the n variables x1, x2, xn. Now, what is u? It's basically like the z that we had before, but now he's calling it u for some reason, and I will stick with that. U is a differentiable function of n variables. Now we are not having x, y only, we're having x, y, z, w, h, j, whatever number of variables you can have. We can call them just, instead of x, y, z, w, we can call them, I want to call them x1, x2, x3, x4, x5. When I have 5 variables, x6, if I have 6, okay. Take this off. Okay, and that's basically what he's doing here. This is x1, x2, x3 up to xn, depending on the number of the number n. And each x is a differentiable function of m variables. So now each function of these, no, give me more space. I will show you what I'm meaning. This is very important. x1, x2, x3, x4, and then it goes up to xn. N is the number of variables. Now each of these have m variables branching from them. So here we have and the variables are called t's. So t1, t2, t3 up to tn. Here the same, t1, t2 up to tn, t1, t2 up to tn. So now this looks like a very, very big chain. And now if you have also more variables, it's gonna be way more branch. I don't want to get into that. Okay, anyway. Okay, so now the general chain rule states that, sorry, okay, having a bit of technical issues here, seems like it. Okay, so now to find the partial derivative here, we have the partial derivative u with respect to ti, partial derivative u with respect to x1 with respect to ti, u, x2, x3. So it's basically what we used to do if we want to find the partial derivative of the function u with respect of one of the variables that are not included in the function itself but are included in functions of the functions. So basically n is a function of x1, x2, x3 up to xn, but not a function of xt1. But these little functions, the x's, are functions of the t's, t1, t2, t3. And then x2 is a function of t1, t2, t3 up to n. x3 function of t1, t2 to tn, and so on. It goes up to xn, which is a function of t1, t2, tn. Never ends, especially if you have a lot of variables. So now we want to find the partial derivative of u with respect to one of these little variables. Okay, and we called it here like ti. It can be t1, t2, t3. Here it's the same. So what we're gonna do, we're gonna go for each term the same as we did. The partial derivative of u of one of the functions of u, or one of the variables of u, and one of the variables of u are x1. So we're gonna take it with respect to x1, and then we're gonna do x1 with respect to t1. So the derivative of x1, we're gonna take it with respect to t1 as an issue. Okay, with respect to one of the variables, and then we're gonna go to the second variable. We can say u with respect of a second variable of u. Okay, and then the variable of u, we're gonna take it as a derivative of t1 of the variable that we chose, the t, whichever t we chose, t1, whether, let's say here for our example t2, let's say we want t2. So here we're gonna take x1 with respect to t2, and then we're gonna have x2 with respect to t2, and so on until xn with respect to t2, still t2. We're gonna define which t we want from the beginning, and then we can have other also functions as these for other t's. So it's maybe it could be hard to grasp at the beginning, but I wanted to try to, to understand. And please don't hesitate to drop us a comment if you don't understand what's happening here. Let's solve an example. This looks like a bit of a messy example. So what do we have also? We have implicit differentiation. Oh, okay, we're almost done. We can survive this example. Let's try to survive this example. I'm with you. I'm suffering with you. Okay. That's fine, it's not suffering. This is math. We love math. This is not suffering, this is math. Or at least I love math. You guys, I'm not sure about you. I love math, even if it has not given me any, have not yielded any return for me. Or maybe it have yielded some returns now. I think some returns, but I haven't noticed them. I'm gonna notice them in the future, and hopefully you too. Okay, now back. We want, so our function is w. Let's rewrite that. Cause why not? RT, so you can see it better. Vu r equals x squared plus y squared plus z squared, and s is cosine xyz, and then t equals e to the xy, and then v is basically tan inverse of y over z, and he is also, wait, we have also u. Y squared this is a bunch of variables. So we want the partial derivative of w with respect to y, and we don't have y in w. As you can see, it's all r, s, t, v, u. We don't have y, so but we have y's in r, we have y's in s, we have y's in t, v, u. So we're gonna use chain rule. So partial derivative of w with respect to the first r, the r with respect to, we want y, so you say y. Partial derivative of w with respect to s, and then multiplied by the partial derivative of s with respect to y also. We using the same, as you can see, the same variable here. The partial derivative of w with respect to t gives us the t with respect to y plus w with respect to v. Whew, this looks like a whole mess. We haven't even started. See here, it's all y's. Anyway, let's start. EW over dy equals, now with respect to r, s plus t, that's it, multiply by dr with respect to y, 2y, plus dw with respect to s, r, plus v, multiplied by ds with respect to y. It's just y minus, let's start the minus first, minus y sine of xyz plus w with respect to t, r times t with respect to y e to the xy plus w with respect to v s plus u. V with respect to y, v with respect to y is 1 plus y over z all squared multiplied by 1 over z. Okay, let's go down. We stopped at v, and lastly we have w with respect to u gives us v multiplied by w with respect to y, which gives us 2xyz, and this is our little answer. Not very little, it's like a big chunky answer. Implicit differentiation, f of xy equals 0. What is implicit differentiation? So we used to have implicit differentiation in previous, if you talk calculus 1, calculus 2, these all included previous implicit differentiation. We had it in one variable or like two variables xy only. This was the simplest version of the implicit differentiation. Now we can have it for more variables. So basically it's saying, since both x and y are functions of f, I think this is a mistake, it's supposed to be f. Since both x and y are functions of f, then we're gonna have the partial derivative of f with respect to x times the partial derivative with x with respect to x plus f over y and y with respect to x. Okay, oh no, actually, since both x and y are functions of x, so x is a function of x and y is a function of x also. And here, this is, as we can notice, dx over dx, this is equals to 1. Okay. But here, as you can say, dx over dx is 1. And if we assume that the partial derivative of f with respect to y is not 0, then we can solve for dy over dx, which is what we want. We want this. If we have a function x, y squared plus z plus y, actually this is the regular implicit differentiation. If you want to find the dy over dx implicitly, okay, since it may be hard sometimes to write y as a function of x, sometimes this becomes challenging, so we need implicit differentiation. So this just basically becomes dy over dx equals, what's gonna equal? It's gonna equal df over dx over df over dy partial derivative. And we don't forget this minus sign since we're gonna move it to the other direction. So this is basically a formula. And this is what we get here. Minus partial derivative f with respect to x over partial derivative of y with respect to y, which is basically minus fx over fi. And that's how we get our partial derivative, or sorry, implicit derivative. Okay, so take the example. Okay, also we can apply the same for more than two variables. Let's take this. Ooh. Solve. dy over dx from the formula is minus fx over fy. And if we want to write fx y equals 0, we're gonna write x cosine of 3y plus x to the 3 y to the 5 minus 3x plus e to the xy. Taking fx gives us, if we want to find fx, we're gonna have 3y equals 3x squared y to the 5 minus a 3 plus ye to the xy, and then fy. What is fy? Fy is basically minus x 3x sine of 3y plus 5x to the 3 y to the 4 plus ye to the xy, 3x regarded as constant. So dy over dx is basically minus, so this is positive cosine of 3y plus 3x squared y to the 5 plus ye to the xy minus 3. I hope this is the solution, and it looks like it is the solution. 3y plus 5x to the 3 y to the 4 plus e to the xy. And that's, my friend, is the solution, is the derivative, the implicit derivative. I love it. I love it. So let's say we have f, x, y, z. We have three functions. Now we're gonna use the chain rule, and this is gonna become 1. But these, what are we going to do with them? If we say that the partial derivative of x with respect to x equals 1 and the partial derivative of y with respect to x equals 0, if we assume it equal to 0, so this is 0, so this term goes away, so we're gonna have almost a similar function or a similar formula, which is, if we assume the partial derivative of f with respect to z is not equal to 0, we solve for partial derivative of x z with respect to x, and we obtain the first formula, the formula for dz dy is obtained in a similar manner. And a note here, an important note also here, these are not regular derivatives, these are partial derivatives. These are partial derivatives, it's a mistake. Partial derivatives, okay. And why did you say the partial derivative of y with respect, the partial derivative of the function y with respect to x equals 0? Because y is regarded as a constant. So, and the derivative of a constant is 0. So that's why we said it's 0. That's the reason. But here we can't say the same for dz, since z is the independent variable, and we want to find this. Okay, so let's say z is the independent variable that we need this. So, and basically this is similar, very similar formula. So it's minus fx over fz. Sorry, this is a mistake from the professor. And then the partial derivative of z with respect to y is minus fy over fz. This is correct. No, this is correct. Yes, so it's basically the opposite. You can say fx, partial derivative of x, fy, and then fz. Partial derivative of z is the opposite, basically. Yeah. Now, if you want to find this, do you want to solve the example? I don't want to solve it. So we're gonna solve it just to make sure we understand. Come on, here's one example. This is our last example. Let's add this. Our last example. Our last example. Don't worry, I'm okay. Equals x squared sine of 2y, 5z, minus y cosine of 6zx minus 1, which is equals to 0. And we want to find dz with respect to dx, which is basically minus fx fz. And we also want to find dz with respect to dy, which is minus fy over fc. Let's check this. I want to check this. Yes, it's the opposite. So if we have x and down, we have x up here. And if we have y in the denominator, we have y here. Like, one way to memorize this, I use this to memorize. So fx equals, gives us 2x sine of 2y 5z. Oh my god, plus 6zy cosine. Gotcha. 6cx. This is fx. Fy. What is fy? 2x squared cosine of 2y minus 5z minus cosine of 6cx, and then fz is just x squared, or minus 5x squared cosine of 2y minus 5z minus 6y or plus sine. Okay, yeah, plus 6y sine of 6cx. Actually, we're gonna have also x, so we're gonna have 6xy sine of 6cx. Oh my god. Now this is very simple. We just substitute. So minus, we just plug in the values that we got, and we get the implicit derivatives. No, I love this. This is amazing. Really. Okay, this is the last example. I promise. I promise you. And I have never broken a promise. Never ever in my life. Maybe once. Maybe once. No, I've never broken a promise. Never broken a promise. Oh, I love this. I love this. And that's exactly how it's done. Thank you for watching. See you on the next lecture. Until then, have a great time.